see the calculation of flux. Calculation of flux. So first we are considering the for uniform electric field. For uniform electric field, as we have discussed earlier, flux is given as electric field into projected area. Projected area. So first of all, what is the meaning of projected area? So when we are talking about the electric field and projected area, so here electric field is uniform. Uniform electric field means if we are talking about the lines of forces due to these field, the lines of forces will be equidistant as well as parallel to each other. So first of all, this is your electric field which is uniform, and we want to find the flux through any particular area. So I kept a cylinder here. Cylinder of radius r and let height h. And now the question is that what is the flux through the cylinder? So what can be said here? First of all, meaning of projected area. So just like assume a light beam in place of electric field. Let light beam is coming here from this side, and if we are having a screen, let this be your screen. So if we are having a screen here, so which type of shape we will get on screen? So that shape will give you the projected area. So in case of cylinder, so if we are projecting a light from this side, and if we are looking at diagram or shape on screen, so we will get a rectangle of with your 2r and height is your h. So projected area will be, we can have, this is the projected area of the cylinder, this height h and 2r this. So this is the projected area of cylinder. Projected area. So the area of this will be your 2RH. So flux. So flux through this written as, the flux is equal to your electric field E into 2RH. This is the flux. And here, if we are talking about the incoming flux, so from this point or from this surface, it is your incoming or coming, and from this end it is leaving. So here we can say incoming and outgoing flux both will be same. Incoming flux here negative, while outgoing flux will be your positive. But net flux through this or flux linked with the cylinder is given as E into 2RH. Similarly, suppose we are having another shape. Let a sphere is kept in uniform electric field. That is sphere of radius r kept in uniform electric field like this. If we are looking the flux through this, electric field your E, radius your r, and on screen, if we are looking the projected area on screen, so we will get a circle of radius r. So here circle of radius r will be the projected area. Circle of radius r will be projected area. Will be projected area. So total flux, again directly we can say the flux will be here electric field into pi r square. So likewise we can write here. Similarly, see another example. Now if we are having a cone and that cone is kept in uniform electric field, let this is our cone of radius r, and height h, and this is kept in uniform field like this. And now if we want to calculate the total flux through this, so when we will see the projected area, so what we will get from here, we will get a triangle of height h, base is your 2r, so projected area will be like this. Triangle of height h and base 2r, this is the projected area. So projected area will be half base into height, this is your r into h. So flux, so flux through this cone will be your electric field E into RH. So in this manner we can calculate the flux if the electric field is uniform. So flux can be written as electric field into projected area. But if electric field is non-uniform, then it is slightly different scene we can say. See, if non-uniform electric field is there, then how to calculate the flux? Second point, the flux through an area in non-uniform electric field. In non-uniform electric field. So for example, let we are having a point charge, and due to the point charge we want to find a flux through a ring of radius r kept at a distance small r. So question is like this: suppose this is a point charge q, and due to this charge, if we want to calculate the flux through this ring of radius capital R and kept at a distance small r. Now if we are looking this point charge, so we will see that this point charge will produces lines of forces radially outward. But as we are moving upside, or as we are moving away from the conductor, so electric field value gradually decreases. So when it reaches to our ring, so electric field will not be uniform. So we cannot use here relation the flux is equal to your electric field into projected area, because if we are looking the different lines of forces, different lines of forces, what we observe, the gap between the lines of forces are also different, as well as direction of electric field is also different. So it is not possible to get a flux by the same method as we did in the previous case, electric field into projected area. So we will calculate the flux from a small segment and then we will integrate. So how to do this one? So we can have a point charge here, and in this ring we are making another ring of radius let y and thickness dy, and since every point on this ring will be at same distance from the point charge, so magnitude of electric field will be same, but direction may be different. So let the angle made by this electric field with the axis your theta, and this is the area vector direction. Electric field you are in this direction, area vector you are in this direction. The angle between electric field and area vector here your theta. So first of all, how much the field value here? E is equal to your 1 by 4 pi epsilon naught q is the charge, and this distance here small y square plus r square, q by y square plus r square, where small r is the distance from the point charge to the center of ring. So this is the electric field. So flux through this area, the flux through this small area is written as electric field 1 by 4 pi epsilon naught q by y square plus r square into area of this ring of thickness dy and radius y. The area of this ring will be 2 pi y dy into cos theta. This is the flux. Now, either we can calculate the flux in terms of angle theta, or we can calculate in terms of the radius r. See, we can write the value of cos theta or value of y from here. See, in this triangle we can simplify this one, 2 pi cancel here, q by 2 epsilon naught y dy by y square plus r square into cos theta. See, in this triangle y by r is tan theta, y by r is tan theta. So dy can be written as r sec square theta d theta. This value we can substitute here. So our whole expression will come in terms of angle theta. See, further we can write here d phi is equal to q by 2 epsilon naught y dy. Y is your r tan theta, dy is your r sec square theta d theta into cos theta by y square plus r square. Substitute the value of y, so r square sec square theta, this value came. Now further we can simplify q by 2 epsilon naught. See, from here r into r square, and this r square cancel, sec square theta cancel, tan theta into cos theta will be sin theta. So this become your sin theta into d theta. This is the flux through that small element or a small ring of radius y, thickness dy. Now theta value depends on what is the maximum or what is the maximum radius here. So let this value we can select alpha here. So then if we are integrating for total flux, the range of theta will be from 0 to alpha. So total flux can be written as q by 2 epsilon naught and sin theta minus cos theta, it become your 1 minus cos alpha. This is very interesting and important result. So phi is equal to q by 2 epsilon naught 1 minus cos alpha, and in this particular example the value of cos alpha can be set. See, from here cos alpha, this is total radius r, this is your small r. So cos alpha is equal to small r by root over r square plus r square. So in this, this is a very general result. This is very general result, and this result we have to remember which angle is your alpha and where is the charge q kept, and particularly in this case cos alpha is your r by root over r square plus r square. Then flux will be written as q by 2 epsilon naught 1 minus r by root over r square plus small r square like this. So this is the flux through the whole ring of radius r kept at a distance small r. And see, this result can be used in different number of places which are very similar to the same situation. See 1-2 example, from that you may get better idea how to use this relation in the further cases. See, so as we saw, the flux through this point charge with a radius, with a ring of radius r can be given by this expression. See, this angle we took here alpha. So flux through this ring is given as q by 2 epsilon naught 1 minus cos alpha, and in terms of position we can put the value of cos alpha like we can put the value of cos alpha as your 1 minus small r by root over r square plus r square. See the how this relation we can use in the different questions here. See example number 1. So question is this: let a point charge kept at the vertex of a cone to find the flux associated with that cone. See, a point charge q kept at the vertex of a cone, at the vertex of a cone of radius r and height h, to find the flux associated with the cone. See the solution. Our question is like this: this is our cone and this is the vertex. The point charge q kept here, point charge q kept here, and this cone have radius r and height h. So now we want to find the flux through this cone. Now total flux through cone, total flux through cone phi is equal to flux through plane surface of cone, plane surface of cone plus flux through curved surface of cone, curved surface of cone. So plane surface means this is the plane surface, and if we are talking about curved surface, this is the curved surface. Cone is like this, that surface is called your curved surface. Now if we are looking at the total flux, so we can say flux phi is equal to flux due to plane surface plus flux due to curved surface. See, if we are talking about curved surface, the curved surface means have area vector this, which makes an angle 90 degree with the surface. Similarly, if we are looking for this part have area vector this direction, this is the angle 90. Now due to the charge, if we are looking the electric field direction, this is the direction of electric field. So what we found here, electric field and area vector making angle 90 degree here. So total flux through this will be your 0, because flux through the any surface is given as electric field into area into cos theta, and theta value here 90 degree. So, flux through the curved surface will be here 0. Now, come to the plane surface. Plane surface means it is very similar to the situation as I have shown here. It is just like a total flux passing through a ring of radius r. So, exactly same result we will get again here. So, no need to derive again and again. So, in place of r, this was the distance from the center of this to the point charge. So, in place of r here we are having your h. So, flux through the plane surface is given as q by 2 epsilon naught and 1 minus h by root over h square plus r square. So, total flux phi is equal to your q by 2 epsilon naught 1 minus h by h square plus r square. So, this is the one of the application of this type of result. See another question here. Now, in this example also we will use the relation whichever we have derived here. So, see, in this example we are taking a charge at the center of a cone, charge at the center of a cylinder, and we would like to find the flux through the curved surface of that cylinder. See, the question is like that: a point charge q kept at the center of a cylinder of radius r and length L, then find the flux through the curved surface of cylinder. This is the question here. A point charge q kept at the center of a cylinder of radius r and length L, to find the flux through the curved surface of the cylinder. It means the question is like this: this is our cylinder of length L and radius here r. So, point charge kept at the middle here, point charge is here. So, we want to find the flux through this curved surface, Now, how to get this one? See, so first we can write total flux through this, through cylinder is equal to flux through curved surface plus flux through plane surface. This is the total flux. The total flux phi is equal to flux through curved surface plus flux through plane surface. So, plane surface are these. This is one of the plane surface and this is another plane surface. We will have two plane surface and one is your, this is curved surface. Again, if we are talking about flux means number of lines of forces passing through a given area. So, here point charge is producing lines of forces like this. So first of all, since point charge kept inside the cylinder, and as we know during the electric lines of forces property, we have found number of lines of forces originating or terminating at a charge is given as Q by epsilon naught. So here point charge Q is kept, so if all the lines whatever this charge is your producing, that all line will pass throughout the whole area of the cylinder. So total flux through whole area including curved path as well as for plane surface, this will be equal to the number of lines generating or generated by this charge. The number of lines of forces generated by this charge is equal to Q by epsilon naught. The total flux through the cylinder is your Q by epsilon naught. But we want flux through the curved surface. Now, flux through the plane surface. In case of plane surface, this is again the very similar case as we have found here. Okay, this is just like a ring, and through this ring we want to calculate, and this angle we can say just like alpha, and this is your L by 2. So, since both the plane surface are symmetrically placed from point charge Q, so lines of forces passing through this plane surface as well as this will be equal, and so whatever the flux from this part, same amount of flux from this part also. So 2 times flux through the one of the part is given by this relation, which is equal to your Q by 2 epsilon naught, and 1 minus here R the distance from the point charge to the center of that, the point charge to this, that is equal to here L by 2. So L by 2 by under root of L by 2 whole square plus R square. So total flux through the curved surface we can write. See, the flux through the curved surface is written as Q by epsilon naught, the Q by epsilon naught, and here Q by epsilon naught will cancel. So what is left here? The Q by epsilon naught into L by root over L square plus 4R square. This is the flux through the curved surface. In this way we can determine the flux through the curved surface by using this relation. So this is the general idea about the calculation of flux. See another example in which electric field is variable but different type of question. See another example. The electric field in a space is given as E naught plus AX I cap. So find the flux through an hypothetical cube of edge L kept in the path of cube, in the path of electric field here. X is the position of point, a position from the origin, along x axis. So here it is given as electric field E is given as E naught plus AX I cap, and A is a positive constant. So first of all, from this expression it is given as electric field your variable, because as x value changes, electric field changes. So electric field your variable, but it is acting along the x direction, and a hypothetical cube of edge L. It means if we are considering this is the x and y axis, and we can say let this is a hypothetical cube kept in the path of electric field, and the coordinate of this we can say x naught, and this will be your x naught plus L. So we want to find a flux through this cube. So first of all, as we are calculating the flux through this cube, so this cube have 6 surfaces. So this cube have 6 surfaces, but if I am considering this is one surface, this is another surface, electric field direction here along positive x. So area vector of this surface and this surface here in this direction. So there is no flux through this surface as well as through this surface. Apart from these two surfaces, two other surfaces, one is this and another is backside of this. This also have area vector in this direction. So area vector in electric field again makes an angle 90. So through these surfaces also there is no flux. Whatever flux, that flux will be from this and this surface. So here electric field in this direction, area vector here this direction, area vector in this direction, and at this point electric field in this direction, area vector also here in this direction. So total flux is equal to your here electric field value E naught plus A, and that is at distance x naught. So E naught plus A x naught into area L square, and since area vector this side, electric field this, angle here 180, so minus sign. Similarly from this part if I am looking, plus electric field will be here E naught plus A, and now position of this point here x naught plus L. So this is the electric field into area L square. Now we can simplify this. So after simplification, minus E naught L square and E naught L square this cancel. Here it become your minus A x naught L square, and this will be your plus A x naught L square plus A L cube. So finally our answer is your flux is equal to your A L cube. This is the total flux through this cube. So likewise we can solve if the another form of the variable electric field is given.